Hey guys, welcome. We're now starting lesson number 2, limits to infinity and continuity. This lesson will be broken down into 3 videos. The first one will be limits to infinity. The second one will be talking about continuity, how to write continuity, and talk about the forms of discontinuity. And then the third video will be on the intermediate value theorem, which is a theorem that requires continuity. So let's go ahead and get started with these first 6 examples. And limits to infinity, if you think about it in terms of what you learned back in pre-calculus, is basically the end behavior model, or when you're looking at a function. So let's say I've got a little graph here and I draw something like this. There's an asymptote here. And let's say this one goes up like this. So if I'm looking at the limit as x approaches negative infinity, then if I have this function right here, let's call this f of x, just because we like f of x. So if I'm looking at the limit as x approaches negative infinity, then this function, as we're going negative, right, negative infinity of x, the y values are exponentially getting bigger and bigger and bigger. So the limit as x approaches negative infinity would be positive infinity. If we were looking at the limit as x approaches infinity from the right, and we're going to call this value for this y is equal to, let's go with d, letter d. So if this asymptote is y equals d, then this horizontal asymptote would be where we restrict our function, and so our limit as x approaches infinity from the right would actually be the value of d. Okay, so really that's what we're looking for. We're looking for limits to infinity. And so we have in this example, this packet right here, examples of what you should already know, behavior versus based on your functions themselves. So if we look at example 1, A, B, and C, the reason why this is all one particular example has to do with the fact that they're all rational functions. And you guys have learned very, very well in pre-calculus, and I think even in algebra 2, that if you were to graph this, right, if you were to graph this, you would want to see that the degree of your denominator is bigger than the degree of your numerator. This means that this is a bottom-heavy function. So what I tell students is that bottom-heavy function represents the function 1 over x. It's just a hybrid of 1 over x. And if you remember what the graph for 1 over x looks like, right, just means that there's at least one more x in the denominator, right? So, and if this had been x squared, it'd be 1 over x squared. You'd still get the same thing. You'd still get like general behavior here. And so if you guys look at this, and you can remember that for 1 over x or even 1 over x squared, there is an asymptote at y equals 0. So if I'm approaching it from the positive infinity, I'm going to get 0. And if I'm approaching it from negative infinity, I'm also getting 0. So if I'm a bottom-heavy function, then this limit is going to be equal to 0. It doesn't matter if this is plus or minus infinity, it's always going to be 0. So if your rational function is bottom heavy, then your limit as x approaches infinity or negative infinity will be 0. Remember, we're only applying this to when we're approaching infinity or negative infinity. If this had been like a 3, then you would try substitution first, and if substitution didn't work, then you would go and do factoring or some kind of algebra content to actually help you simplify this down. All right. So if we look at the second example that we have here, we see that the highest degree in the numerator is actually equal to the highest degree in the denominator. Now, I just want to say really quickly that, don't always assume that it's the very first term. If this had been a 9, right, instead of a 5, then your highest degree in your numerator would be higher than the highest degree in your denominator, right? So if you're looking at this, then you can look at 3x to the 7th over x to the 7th. Why are we able to get rid of the rest of this stuff here? If you're approaching infinity, this is going to be the fastest thing to go to infinity. So if you have, I always use the example, if you're going to go and do, let's say at the bottom, x plus 5. Let's say that's the bottom. And we really just care about the x when x approaches infinity, because if we're substituting infinity here and we're simply adding 5 to that, that's not going to really make a difference. So you're only looking at the highest degree in the numerator and your denominator. And so if we were to do this, then we would simplify this down to 2/3. You guys know from Algebra 2 and pre-calculus that there's a horizontal asymptote at y equals 3/2. Well, if there's a horizontal asymptote at 3/2, like I said right here in this example right here, that means that we have a M behavior at that value. Again, just like in example number 1, it doesn't matter if it's positive or negative infinity. Your answer to this problem is going to be equal to the ratio of the leading coefficients of your functions. So it's just 3/2. That is a 2, even though it kind of looks like a 3. So 3/2, or there's your answer right there. All right. And then the last one, like I said, I hope this is, just making you guys like remember what we've done in, back in pre-calculus. We have the degree in the numerator is greater than the degree in the denominator. Well, in this case here, there is no horizontal asymptote. It's a slant asymptote. And you should say that, okay, well, it does not exist. But what you want to do, because again, usually they want a positive or a negative infinity. So this is what I tell students to do. Again, everything that I'm writing down here is kind of like my side work. I'm not really doing too much. But again, I'm taking this and I'm abbreviating this to look at x over 2, right? I'm just simplifying this down. So I took x squared on the top and x squared on the bottom, and I got this. So this can be rewritten as y equals 1/2 x. So that means that the asymptote is similar to the function 1/2 x. Well, this is what I tell students. We're looking at x approaches positive infinity. Well, this is going to go towards positive infinity. As I move my graph, it doesn't matter if I'm going above it or below it, I'm going to positive infinity. So I know that this answer is going to be positive infinity. If this had said x is approaching negative infinity, then both of my answers would be, my answer would be negative infinity. If this had been a negative x cubed, a negative right here, so it'd be negative 1/2 x, my slope of my line would be this direction, and then these would flip-flop. So it's not always positive infinity, negative infinity. But that's the general idea for this. So bottom heavy, always 0. The easiest example you can do. Again, if it's the leading coefficients, the ratio of the leading coefficients is the answer if your exponents are both the same. And then if it's a higher degree in the numerator, you just got to do a quick simplifying and just look at the slope of the line. If it's going positively, positive goes with positive, negative goes with negative. If it's a negative slope, then positive goes with negative and negative goes with positive. So that's the idea for rational functions. Okay, so let's go ahead and look at example number 2 and number 3. I want you guys to see that they are really, really, really similar. I want you to look at this, and again, look at the highest degree, and in this case here, it is 5. If you look at this one, you got to be really careful. The highest degree is actually the middle term, that is a 6. So what are we getting out of this? So this clearly is a polynomial, and when we're looking at this, we have an odd, so the exponent tells us that we have an odd polynomial, and then the leading coefficient, we don't really care that it's a 9. What we really care about here is that it's negative, right? So we have an odd negative. So what I tell students when I taught pre-calculus is that, okay, you always want to think about the very basic graph of y equals x cubed, because that's an odd function. But since it is negative, instead of going like this, right, we want to go like this. This right here. So all odd negative polynomials have the M behavior that represents y equals x cubed. So if I'm looking at x approaches negative infinity, then my eyes are going to go towards negative infinity, right? So x is getting smaller, and so this answer is going to be equal to positive infinity. If I had said x equals positive infinity, then I'd be going down like this. If this had been a positive 9, then my axis would go like this, and then positive would go with positive, and negative would go with negative. All right. If I look at the next example, here I have, again, an even highest degree. So this is my even. And I also have the fact that the leading coefficient is positive. Actually, let me make sure it's positive. Okay, good. I couldn't see from what I did. So it is positive. So I've got positive and even. So again, I tell my students, think about y equals x squared. And so since it's even and positive, I'm going to draw it like this. If it were negative, I would just flip it across the x-axis. And so no matter what this is, if it's positive or negative infinity, I'm still going to positive infinity, right? So both directions are going upward like that. So these are simple polynomials. All we really care about for these is the highest degree of the power, and then literally the sign in front of it. So we don't care about anything else in our problem except for the highest degree. All right, that just gives us our end behavior of what our function is going to do. All right, so let's look at example number 4. For example number 4, you have to, so another classic example for limits to positive and negative infinity is parent functions. So if you look at the parent function e to the x, as a calculus student, I'm 100% expecting you guys to know your parent functions and also transformations. Now, I will tell you guys that we're not going to do crazy transformations like you guys probably did in pre-calculus and maybe algebra 2, but I need for you to know that this -3, this -3 right here, moves this down 3 units. Not only does the function get moved down 3 units, remember that for the graph e to the x, there is a horizontal asymptote right here at y equals 0, right? And so if I'm going to move it down by 3, my asymptote actually moves down by 3 as well. And then my function also does that. So we're looking at, I should get to that point, but it's okay. We're just doing a rough sketch here. And you guys don't need to show work for this. I'm just trying to show you guys how to think about these kind of problems. So now we have, this is the idea. So now this right here is the graph for y is equal to e to the x minus 3, right? That's what this graph looks like. So now if I'm asking you guys to look at x approaches negative infinity, well, just like in the previous examples, you want to look at what's happening as my graph is approaching negative infinity. So as x is getting smaller, well, it's approaching this asymptote here. So in this particular case, this asymptote is at the equation y equals -3. So this answer would be -3. So we can kind of see that asymptotes also are important. We're talking about end behavior, right? Now, can we cross the horizontal asymptotes? Yes, you've done examples with that. Will this ever cross the horizontal asymptote? No. No, it will not. All right, so based on the function that you see, e to the x, right? This can never be negative. So this is the highest, the lowest value it would ever be. This can never actually be 0 either. So we're good. All right. Okay, let's go ahead and do example number 5. So when I put example 5 in here, this is one of those where you would like to graph. The identity for this is actually nice. We will do something called L'Hopital, and I think I've mentioned that in lesson 1. That's going to help us a little bit better understand this, to understand this actual limit. But x approaches infinity of cosine of x over x. So if you actually were to graph this on your calculator, then you would see that it goes and oscillates back and forth, back and forth, back and forth. But as it does, it's going to get really, really, really close to 1. So it's kind of like a, sad to say, like a little flat line thing going on here. So it's going to get closer and closer and closer to 1. So this was very similar to the table example we did in the first lesson, where we're back and forth, but we eventually do get to 1. So I'm not a big example. I'm not expecting you guys to know this right now without the fact that you just have to graph it. But I want you guys just to see that sometimes it doesn't have to be like this nice flow, right, where it's going to be always on the same side of the asymptote. Sometimes you plot points, boom, 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 but it's getting closer and closer and closer to 0. So in this particular example, that's what's going to happen. And then the last one is question number 6. And to be completely honest, students, they have to know what the graph for the inverse tangent is. And again, as a calculus student, I do expect you guys to know very basic stuff. What the inverse graphs for sine, cosine, and tangent are. You don't even really need to know them for the other 3. But when you're graphing the arctangent, then you have to remember, and again, it's just me refreshing your memory. Hopefully you remember it looks something like this, right? And this will be a non-calculator problem. And so if I'm asking you guys to look at this function as it approaches negative infinity, well then, like before, I'm telling you as x is getting smaller, right, then we're going across this. So our value is going to be, our answer for this problem is going to be what this is right here. And I hope that you guys realize that this is bounded. This is bounded by pi over 2 and negative pi over 2. So this answer, there is no work for it. It's just the fact that you know what the graph for the arctangent looks like, and you know that its range is from negative pi over 2 to pi over 2, right? So that's hopefully helpful for you there. So just basically knowing parent functions, and even arcsine, arctangent, or cosine is also important. Like I said, even in BC calculus, we don't really get into the arcsecant, cosecant, and arctangent. So I think we're good with that. Okay? So what did we get out of that? What was the whole point out of it? And the whole point of that is the fact that horizontal asymptotes does a really good job of indicating limits to positive or negative infinity, right? It's just going to be what that y value is that we're approaching, but we never get to, okay? We never get to. And so we have it where it could just be, below the axis, again, below it, and then, here we can go back and forth above it, but it's still the end behavior is going to be the same. So even in this example right here, the end behavior is going to be whatever this value of L is. All right. Okay, so let's look at the actual limits involving radicals. So just like we did in example number 1, 2, and 3, or sorry, example 1, A, B, and C, we're going to do the same thing down here. We're going to look at the highest degree in the numerator, which is x, and then the highest degree in the denominator would be the square root of x squared. This example is actually a really good time where we really don't care about this -1. The example I tell students is that, you're given $1 billion, and then they're like, that's not enough money, so let's square $1 billion, and that's what you're going to get. And so if you have 1 billion squared, which is a huge, huge, huge number, you're not going to be, at least I hope not, you're not going to be mad if then 1 billion squared, you lose one small dollar. So in the whole grand scheme of things, it's not going to really matter at all. So we're looking at this, and so we're left with x over the absolute value of x. Now clearly this is going to cancel down to positive or -1, right? The x's would cancel out. You just have to take into account the fact that this is a positive infinity. You already know that this bottom is going to be positive. There's nothing that ever can be put in here that's going to make this negative because you're taking the absolute value of it. Since this is positive, then this is also going to be positive. So you have a positive x over positive x. So really what I did here is I substituted in infinity into this just to get what sign I have. But then I left it at just simply x. Well, the x's cancel out, and then you're left with the fact that this is 1. Right, so this actual limit is 1. If we look at the second one over here, again, all of this is just scrap work here. You have 2x in the top, and then the very bottom you have the square root of x, the square root of x squared. So we're just going to go ahead and skip this step and put it right here. Students ask me, what if this had changed? If this had been x to the 4th, then this would be x squared. You don't have to have the absolute value because anything you put down here is going to be positive. If this had been x cubed, then you would have to take the square root of x cubed, and then you would just have to do what I did over here and just pay attention to the sign, because all we really care about is the sign. And then you'd also have to worry about the property of exponents, that you have an x over x to the 3/2. I'm saying more complicated stuff than what it is. Usually it's pretty straightforward like this if we're going to do it. And so we have our 2. We notice that we have a negative infinity right here, so this is going to keep this as a negative value for x, right? Because this is going to plug in, so x is getting smaller and smaller and smaller, so this value here has to be equal to a negative value. And this down here is always going to be positive, right? There's nothing that's going to make this negative, and so when we do this, we cancel out the x's, and so what we're left with here is -2. The only thing that I want to say that some students mess up a little bit about this, if I had added a 9 right here, we have to remember that we do take the square root of that function, right? We take the square root of that function, and so our new answer would be -2/3. So just be very careful that we take into account, just don't pull the 9 out. And again, we don't care about this 4 right here because we're taking infinity and squaring it, and we're adding immediately 4. And again, we're taking infinity and doubling it and adding 5. So these numbers right here, it doesn't matter. And if this had been, a 4x would not have mattered. Okay, it would not have mattered because then our highest degree would still be this x squared, not the x. All right, so what kind of challenging question? What would be a little bit crazy for us? So this is the 9th question. This is the last question we're going to do in this video. Talks about what if we take the limit of something that's not a rational function, but it has a radical in it. So we have infinity, we have infinity, we have infinity. So most likely, like, oh, this answer is infinity. It is clearly not infinity. Okay, there's actually an asymptote in this function. There's actually a low bound that we would actually get. Well, how do we do that? Well, this is where, again, and guys, again, I wouldn't test you on something like this per se. I just want you to see, like, in higher level maths, maybe they would have you do something crazy like this, but I want you just to get familiar with what's happening. So what we're going to do here is we're going to put this over 1, and that's okay, that really doesn't help us, but we want a rational function, okay, because we need to do something with this. And so what we talked about in lesson 1 is how we want to simplify this is we want to multiply by the conjugate, right? So this is going to be plus 3x. Now, just if we multiply the top by this, we also have to multiply the bottom by this, which means we really haven't changed our problem, right? Because we're multiplying this whole guy right here by 1, so we really haven't changed our problem per se. And then we're going to keep our notation. We love notation for this, positive infinity. So the top, ladies and gentlemen, is going to be, it's a difference of 2 squares, so it's going to be 9x squared plus x minus, and you guys can see this right here, it's going to be 9x squared. And that's awesome for that to happen. And then this is just multiplied by 1, so we're just going to go ahead and leave this alone. Okay, so that's our second step. And so let me just simplify it a little bit more, make it look a little bit better for us. So the limit as x approaches infinity, the top part is x. And again, I'm going to leave everything else alone here. And now I can incorporate what we just talked about in the previous example. So the highest degree in the top is x. So here's my little work, my side work. The bottom, this little piece right here, I now have the square root of 9. I knew this was going to come up somewhere. So it's going to be the square root of 9x squared. So this is going to be 3 times the absolute value of x, right? Well, where students mess this up is that this right here is going to be in terms of x. We also have an x here. We also have a 3x here. So we have to incorporate that as well, right? So this is an x term. This is a degree of 1. This is also a degree of 1, even though it's the absolute value of that. And so now I'm going to take this and, this is approximately, like now we're getting a little bit of this. So approximately this, and because this is positive, everything in this is positive. And so we're left with 1 over, let's just do this, x over 3x plus 3x. So technically, I should have the limit down here if I've still got variables. Remember, if you still have variables, you always want to bring the limit down with you. And that's just going to end up being x over 6x, which just simplifies down to 1 over 6. So this limit is actually equal to 1 over 6. So who knew, right? Like I said, this is not something that I would imagine that this would never be on the BC exam. But like I said, it's just nice to see the algebra skills come into play here. All right. So that's my little lesson 2, video 1 on limits to infinity, and we will come back and do part 2 next, which is just the definition of continuity and talk about the types of discontinuity with it as well. So I will see you guys in the next video.